Yeah, it's no problem.
No problem. Thank you. Okay, so far we talked about a Brownian particle, right, which is in a liquid of viscosity, and this particle had some radius r and some mass m. And it also had a friction coefficient against the fluid. And we talked about the consequences of the Brownian motion of this rigid spherical particle, right? This is a rigid spherical particle. Now, what we are going to do today is, instead of thinking about a rigid spherical particle, we want to think about a flexible polymer chain. It looks like that. This is a flexible polymer chain. Let us assume, as an example, let's assume it's a Gaussian chain. This is going back to our very first couple of lectures, where only chain connectivity is included. There's no extra volume interaction, no semi-flexibility. So today we are going to talk about the dynamics of this polymer chain in a liquid, of course. This is in a solvent. Right? And the solvent has a viscosity eta 0. The chain has n Kuhn lengths. And L is the Kuhn length, segment length. So that is our goal. And since you know N, you know the mass of this polymer. So you could think in terms of a mass of this polymer. And this polymer chain is undergoing, of course, friction against the background. Therefore, there will be some viscosity. So what we are going to do is, we are going to talk about not only the center of mass motion of this polymer chain. That's what we talked about for the Brownian particle, center of mass motion, right? It undergoes a diffusion for long enough times. Here, given the nature of the polymer, we can also talk about the motion of a particular labeled monomer, say this monomer, right? How does it move around? In addition to the collective motion of the center of mass, somewhere here is the center of mass. See, this is center of mass, and this is a labeled monomer. We can label a particular monomer inside the polymer chain, and we could look at the dynamics of this labeled monomer, not necessarily this labeled monomer. It could be that labeled monomer or this labeled monomer. So we're going to talk about the dynamics of a labeled monomer as well as the dynamics of center of mass of this polymer chain. And we'll talk about how to interrogate them, how to measure the motion of a labeled monomer and motion of center of mass using light scattering, for example, or X-ray scattering, neutron scattering. We are going to use dynamical scattering techniques to figure out how these movements take place. Of course, you can also measure optically. You could label one of the monomers, say for the end of a monomer, with a fluorescent tag, and we can watch how it moves around. And we can also label all of them, all monomers, more or less, most of the monomers of the chain, and measure how center of mass of this chain moves around. So we can do all those measurements. But before that, we need to have a clear understanding of the physics of this problem. How does it take place? The way we are going to do is to follow the same technique that we did for Brownian particle. And what did we do for the Brownian particle? For the Brownian particle, we did, right, the mass of, let me, for example, let me write down the mass of monomer. Okay, so the Newton's law again, right? A mass of a monomer, which I'm going to write, since I have m for the mass of this, and then also this labeled monomer could be with a given a symbol like m. So I'm going to write this m of the bead, or m of a segment. Now, what do I mean by this? Okay, if I take this Gaussian chain representation, what I will have is this. So here is a segment. So here is one segment, right? There's the next segment is going to be like this. These are Kuhn segments, right? Let me call this to be 0th end. This is 1. This is my first segment, right? That connects one end to the position of the last monomer in that segment, in this Kuhn segment, okay? And similarly here it's a 2, and then I have something like a 3, right? This is the third segment, and on, right? And eventually I'll have, let's assume I have, this is my last monomer. In other words, this is the last segment, but that point is the last monomer of the last segment, right? So this is my Kuhn chain, as you remember, right? This is the various number of Kuhn segments, and they are labeled like this. So when I write MB, that is the mass of one of the segments, okay? Let me write the dynamics for the ith segment. Okay, I is between 1 and n. When I do this, mass times acceleration, and therefore I'll have d squared, or for the ith segment, I write it to be I at time t divided by dt squared, right? Second derivative of the position, d square ri by dt square. That's the first derivative of the velocity. Velocity is first derivative of the position. So that is the inertia term, right? We talked about inertia. Then we have friction term, right? Each segment is going to have some friction term, which I'm going to write as zeta. Please remember, the zeta I wrote before for the Brownian particle is for the whole particle. Here, I'm writing the friction coefficient for only one of these labeled segments, right? Labeled monomer and segment I'm using interchangeably, right? Zeta is friction coefficient for one segment times the velocity, which is a d ri t by dt. That's the friction coefficient from the velocity. And this is equal to the random force acting on the ith segment at time t. So far, this equation is exactly the same as what we had for a Brownian particle, assuming that every segment is another Brownian particle. The ith segment is a Brownian particle because there are solvents around it, it's undergoing random motion. But on top of that, this is random force, of course. But on top of that, this ith monomer is connected to its next segments. This is I plus 1, and this is I minus 1. So there is a chain connectivity that appears for a polymer chain. So in addition to all the forces we had before for a Brownian particle, where now we are taking each segment to be a Brownian particle, there is also a chain connectivity. So I'm going to write this chain connectivity term to be, right, plus d by, this is, you know, the chain connectivity, there's a force. That force on the right-hand side, if I write the force on the right-hand side, force is equal to mass times acceleration. And then I bring it to the left-hand side. Force on the right-hand side is a negative gradient of the potential or free energy. So here, when I bring it to the left-hand side, it will plus d by d or I. And then there is a free energy, which depends upon all the configurations, all conformations of these various segments. Or J, let me write Rj. So this term is chain connectivity. And this term is a friction. And this term is a random force. So only change that we make, but it's extremely important, is to include the force coming from chain connectivity. Okay, so this is a general equation that we need to solve. And as you can imagine, that it may look very difficult to do, right? But we are going to make an exact calculation. Right. In general, it turns out for polymer chains, the inertia is the contribution inertia is very weak. Right? Particularly since we are going to be interested in time scales, which are not going to be, right, very, very tiny. For polymer dynamics, the time scales are pretty long because it takes the polymer chains to relax, move around. For those conditions, we are going to be interested in frequency region. It's going to be into zero frequency region, low frequency region. For low frequency regions that we are interested in, it is possible to ignore this term. We can ignore that. Because when you go to very long enough times, relative to all other terms, see, look at this 1 over time square. For long enough times, this may be not that important. But it is possible to solve the problem, even including this acceleration term, inertia term. It's easy to do, but that is not necessary for most of the situations that we are interested in. Therefore, what we have to do is we have to solve this equation. We need to understand this equation, right? And I'm going to give one example of how to calculate the force coming from chain connectivity. That's what I'm going to do first. Okay, and how do we do that? We already have enough experience with this. You know that for a Gaussian chain, force, before putting a force, a free energy, right? Or even before that, if you remember the free energy, that'll be great. But I'm going to tell you about the probability of a realization of a configuration. This is a probability of realizing a conformation. This is equal to e to the minus, go back to the very first 2 lectures. This is equal to e to the minus 3 divided by 2L squared summation over J from 0 to N, where J runs from here, right? 0, 1, 2, 3, up to N, right? J 0 to N, and then we have Rj at time t minus Rj minus 1 at time t squared. Okay, this is the Gaussian chain, right? That is every segment, right? That's a position of the end-to-end distance of a segment. Okay, Rj minus 1, and you square this, and then with the exponential e to the minus that factor, we get the probability. And therefore, we also calculated the free energy of this. Therefore, the free energy that we are looking at, free energy, which I wrote down here, this is the free energy, Rj, free energy is, you know that, right? Minus kBt logarithm of this P. Okay. So apart from constants, then, therefore, this is equal to some constant term, which we worked out long time back, almost a month back, a constant term, 2 months back probably, constant time plus, what do we have? Plus, from this term, logarithm of exponential is that term, and this squiggly bracket, sorry, symbol that I wrote down, the similarity symbol that that number comes here. When I take the logarithm of that prefactor, I get a constant, and then negative kBt, so we get something like 3 kBt by 2L squared times this summation over j, 0 to n, Rj minus Rj minus 1 squared. So that is the free energy. Okay. So what we need to calculate is, we have to substitute that expression for free energy in here and take the derivative with respect to, see, the ith segment that we are trying to solve this equation for. So we substitute the expression for f and then take the derivative with respect to I. Now, Ri. How do we do this? To give you an example, let me do, suppose I'm interested in I is equal to 10. Suppose I'm interested in 10. Let, for example, consider R, say 10, for example. So I go and look at the derivative of this expression. Okay, let's do this. D by dr 10 of this free energy what is this equal to? 3 kBt by 2L squared. That's a common factor. So let's work it out. So if j is equal to, say, 12, j in this summation, j is equal to 12. So I get R12 minus R11 square. When I take the derivative with respect to R10, that term will not contribute because this is R12 minus R11. It does not depend on R10. So that's not going to contribute. Similarly, R13, R14, that's not going to contribute. Similarly, when I have R7 minus R6, that's not going to contribute either. The only term in this sum that are going to contribute to this derivative would be those which contain R10. So that will be like R11 minus R10 square. Then I'll have R10 minus R9 square. Only those two terms in this sum that are going to contribute. So now let's take the derivative when j is equal to 10. Or let's take j is equal to 11. J is equal to 11, right? Then I have R11 minus R10 square, that will contribute. So R11 minus R10 square, the derivative of that would be 2 times R11 minus R10, right? And then I have to take the derivative once again, that will give me negative 2. Okay, the derivative of R11 minus R10 square with respect to R10 would be negative 2 times R11 minus R10. Now let's go to the next term, R10 minus R9 square. So let's take the derivative of that. That will give me plus 2, right? R10 minus R9. That's what we get. Okay, taking the simple derivative, right? So therefore, what I get is, this is equal to let me bring my negative sign outside, right? And there is a 2 here, 2 here, they will cancel out. So I have negative 3 kBt over 2, oh, sorry, no 2, 3 by L squared, 3 kB2 by L squared. And then let's write down, since I have brought negative sign, I have R11 minus 2 R10 plus R9, for example, right? Because I brought a negative sign out. So negative 2, that means I have to multiply this by negative sign. So I have a negative R10, another negative R10, and then plus R9, so you get this result. So in general, I could write, suppose I'm interested in mth monomer. Instead of this, suppose I write D by D or M. Mth segment instead of 10, M is arbitrary. Okay. F that's equal to negative 3 kBt over L squared. And now you get the idea. Or 11 is 10 plus 1. So M plus 1 minus 2R M plus R M minus 1. Okay. So what we have done is we have derived an expression for the derivative gradient of the free energy coming from chain connectivity. So we have an expression here. Here we were looking for I, but I is a dummy variable. So, right, I is the ith segment. And then now I have gotten in general, I have gotten in general for any segment. Instead of M, I could have put I. Then it will become I plus 1, I minus 1. So what we have then is, going back to this equation, I'm going to rewrite it once again. I'm going to ignore inertia. I have friction term, I have chain connectivity term, and I have random force. And let me write this for, say, mth monomer, or the mth segment. Therefore, for mth segment, the equation of motion is let's work it out. Zeta d or m at time t by dt. Okay, that's a friction. And then from this term, we have minus 3 kBt, right? That's equal to, let me write down from the chain connectivity, minus 3 kBt by L squared, okay, or m plus 1 minus a 2r m plus r m minus 1. Okay. And that's equal to the random force, which is F m t. This equation, right, as you know, the red term is friction, the blue term is a chain connectivity, coming from chain connectivity, this is random force. This model that we have constructed is called Rouse model. Okay, this is called Rouse model of dynamics. And this equation is, of course, it's called the Rouse equation. Now, if you know, this is differences, right? There are two differences, right? M plus 1 minus Rm minus Rm minus Rm minus 1. So this is actually, if you go to a continuous notation, that is, if the chain is very long, instead of taking 10, 11, 12, you can go to a continuous notation. If you do that, this quantity turns out to be written to be, I can write it, going to continuous notation. For the segment variable, we will have the following expression. Zeta d or m times t minus 3kbt over L squared d squared or m at t by dm squared. Okay, and that's equal to f mt. So basically what we have is time derivative minus a second derivative of this quantity that we are interested in, that the position of the mth segment, the second derivative with respect to the segment variable m. This is a very standard equation to solve. You must have seen this in your high school, undergraduate programs, right? It's very easy to solve, except now this right-hand side is a random force. And we know how to deal with random force because we worked out the Brownian motion of a rigid particle. So all that we have to do is to solve this equation. It is convenient to solve this equation if you do Fourier transform of this. Okay, you can solve. We can solve this equation using Fourier transforms. So I'm going to introduce the Fourier transform. That means what? That means I take R M T. I write this as a Fourier series. Okay. I'll write in terms of some variable P is equal to minus infinity to plus infinity. Okay. And the Fourier variable conjugate to RMT, I'm going to write this to be, say, R hat P at T, and then cosine of, for example, pi P M over N. Cosine. Right. So I'm writing RMT as the position, the movement, the position of the monomer to be a collection of cosines. And the cosine is an oscillatory, right? You know what cosine is, right? So it's a bunch of cosines where the amplitude of those waves is given by RPT. And then the M that I'm interested in appears in here. And then N is the number of segments. And P is a variable that goes around. Okay. And what we call this one, we call this to be Rouse modes. This one we call to be Rouse modes. Because there are P, right? P 1, 2, 3, 4, etc. Right? Now, there is also an inverse of Fourier transform. Namely, I could write RPT or at PT is equal to 1 over N integral dm 0 to N. And of course, you know this, right? Inverse of Fourier transform. Therefore, this would be RMT, and then again cosine of pi P M over N. Okay, these are the Fourier transforms. Okay, so I'm able to say I derived the Rouse equation based upon chain connectivity and friction. And then I have this partial differential equation, and the standard method you can use easily to solve is using the Fourier transform. And in the Fourier transform, I write RMT in terms of these Fourier modes or normal modes, if you like, which we'll call Rouse modes because these modes are coming in the context of this Rouse model. And then they are related. RMT is given in terms of it's a Fourier transform RPT, which is given in terms of the inverse Fourier transform. RPT is given in terms of RMT. Right. Now let's look at the consequences of this definition. Now P, right? RP is a Rouse mode, but I'm going to define P is a Rouse mode variable. I'll call it P can go from 0, 1, 2, until n. These are Rouse mode variables. Rouse mode index, if you like, or variables. So what's the meaning of these variables? Consider the case P is equal to 0. What does that mean? What does P is equal to 0? What does that mean? Let's go and look at this one. So I have, suppose a P is equal to 0. Okay. Let's look at the bottom equation. I'm looking for the Rouse mode corresponding to P is equal to 0. I go to the right-hand side and I look for P, and as that say, P is equal to 0, then I have cosine of 0. And you know cosine of 0 is 1. Cosine of 0 is 1. Therefore, what I have is this P is equal to 0 Rouse mode means 1 over n, and then sum over all the segments, positions. Some of right, going back to this cartoon that I drew, right, this is the position of that, position of that, position of that, position of that, and on and on and on. So I add all of them and I divide by total number of segments in it. That is center of mass motion. That is the definition. If a cosine term is absent, this right-hand side is the definition of center of mass. So that means this is equivalent to center of mass motion. Okay. That's the meaning of this. Now let's go and look at P is equal to 1. Okay. And some of you might be thinking, what happens if P is equal to -1? Because my summation goes from -infinity to +infinity, correct? Therefore, instead of +1, what happens to -1? If you go and look at this, you have the P, right? This P appears in the argument of cosine. And you know that cosine is an even function, right? Cosine of x is same as cosine of -x. Therefore, P is equal to 10 and P is equal to -10. They have the same weight, the same contribution. So therefore, we don't have to worry about negative values of P, because the meaning of P is equal to 2 would be also same as P is equal to -2. So now let's look at what does P is equal to 1 mean. P is equal to 1. What does that mean? This means, imagine I take this chain, right? The chain starts from here. So one end is here and another end is there. Here. This is your length of the chain. It starts from 0 and ends with n. Right? And P is equal to 1 corresponds to a vibration, a normal mode, which spans the whole arc length, whole contour length of the polymer chain. It goes like this. This means that is, I take a string and then suppose I strike it, and then the vibration would be throughout the contour of the chain. this corresponds to P is equal to 1. On the other hand, for P is equal to 2, suppose I take P is equal to 2. When I take P is equal to 2, then I look at half of the chain. So now it will be something like that. This corresponds to P is equal to 2. And on and on. Suppose I have P is equal to 3. Right? And this will correspond to like that. That's P is equal to 3. So basically, right, I take my polymer chain and then look at various length scales on the contour of the chain, along the backbone of the chain. P is equal to 1 corresponds to the whole polymer chain. P is equal to 2 corresponds to half of the chain along the backbone of the chain. And P is equal to 3, 1/3, etc., etc. So these are the Rouse modes. This is what we mean by Rouse modes, physically. And mathematically, that's given by this Fourier transform. When I say RPT are called Rouse modes, what do I mean by here is physically when P is equal to 0, whole center of mass of the chain is monitored. When P is equal to 1, the whole chain along the contour of the chain is undergoing dynamics. We're exploring that length scale. And then when P is equal to 2, we look at that one. And P is equal to 3, we look at 1/3 of this, on and on and on. For example, when P is very large, say P, for example, P is, say, N. Okay. Then what I'm looking at is like that. And that is P is equal to N. That is, I'm looking at excitations, vibrations within one segment, comparable to one segment. Okay. So what we do then is we can write, going back here, using these Fourier transforms, we can put it back in here. We can rewrite Rouse equation in a Fourier mode, or we can rewrite this equation in Rouse modes. If you do that, we get the following expression. Zeta, right, d r hat p at t divided by dt. That's a friction term. Then we have the chain connectivity term. That turns out to be 3 pi square kbt by L square P divided by N square. Then I have RP at T, and that's equal to F hat P at time T. So what we have done is basically, there's a second derivative term with respect to the segment index M is written by its a Fourier transform. You know, second derivative goes like the Fourier variable square. So P by N square, where P is the pth mode, and you know the meaning of P. When P is equal to 0, center of mass, right? And clearly for center of mass, this term will go away. And then when P is equal to 1, I'm looking at the vibrations of the polymer chain, the fluctuations of the conformation of polymer chain dynamically over the whole contour length of the chain. When P is equal to, say, half, I'm looking at only half of the chain. Okay, so this is an equation that is derived, and we have now derived this. Okay, we have derived this equation. So now what we'll do is we'll look at the consequence of this equation. And I will not work out the details of the next derivations, right? But I'll give you the results. But the way the results come about is based on this equation. This is the equation. This is in Fourier transform. This is the Rouse equation. Again, this is the Rouse equation. Okay. All right. I think we should probably take a break here before we go into the consequences of this Rouse equation. So we are from now on, we are going to talk about the consequences of this Rouse equation. Okay. June Fang, I think I'm going to take a pause. I'm going to stop sharing here and I'm going to take a pause.
We'll have 1 minute break.
Can you see the screen? Yeah. Okay, good. So look, we have a very nice, simple equation, right? By looking at this equation, you can get lots of information right away. Please remember the way we identified relaxation times for any problem. We did a dimensional analysis. See, what do we do? We had, for example, time in the denominator here. In the numerator, we have RP hat. In the numerator on the second term, we have RP hat. So if we bring this zeta downstairs here, and then this collection would be reciprocal of time. So we can immediately identify what the characteristic time is. Okay, let's call that characteristic time for the pth mode as Rouse time. Okay, so let's do that. If we do this, maybe I should rewrite this equation once again for convenience. Zeta RPT by dt plus, what's the equation that we had? All right, 3 pi square kb t over L square. Then we have p over n square rp hat t, that's equal to f at pt. So let's bring zeta downstairs in here. So I will write this to be d rp at t divided by dt plus, I will write this to be rp at t divided by tau p, because dimensionally it has to have the meaning of time. That's equal to fp t divided by zeta, where tau p is equal to, you can work it out, right? Tau p is equal to, zeta is coming down. I brought zeta downstairs here. So I have zeta L square, and then I have n square divided by, because in the denominator, right? Tau p is in the denominator, square. Then I have 3 pi square kb t and 1 over p square. That's what we have. These are called Rouse. See, look at the P is, you know the meaning of P. P means this. P means the fluctuations or vibrations over different length scales along the contour of the polymer chain. Therefore, what we have is, depending upon P, the value of P, tau P is defined. And notice this, temperature appears here in the denominator, a friction coefficient appears in here in the numerator, and then segment length, and then number of Kuhn segments in the polymer chain squared, n squared. Okay. This expression is called the Rouse spectrum. This expression is called Rouse spectrum. Okay, let's think about this physically. Right. Let's go to P is equal to 10. Compare that with P is equal to 1. Okay, when P is equal to 1, I have excitation over the whole chain. P is equal to 10, I have excitation over only 1/10 of the chain. So the relaxation time for 1/10 of the chain will be shorter than the relaxation time for the whole chain. That physical intuitive argument is captured in this boxed equation, because if P is equal to 100, say 10, P is equal to 10, 1 over P squared would be 1 over 100. So the relaxation time of a segment of a portion of the chain which has 10 segments would be only 100 times smaller than the time needed for the whole chain to relax. That quantitative impression, intuitive argument, is captured by 1 over P squared term. Therefore, the longest relaxation time appears for P is equal to 1. Therefore, the longest relaxation time right, is for P is equal to 1, which we call Rouse time. Which we call Rouse time. So we write it tau R is for Rouse. This is for Rouse. That's equal to, right? You take this box equation, put P is equal to 1. Okay? That's going to be zeta L square N square divided by 3 pi square KBT. Okay, this is a Rouse time. But the important thing you should recognize is it depends on 3 experimentally important quantities. One is the friction coefficient of the monomer, the friction coefficient of your segment, right? Monomer segment or Kuhn segment. And then proportional to molecular weight square divided by temperature. So if the temperature is high, the relaxation time, Rouse time, is short. If there is more friction, if you put your polymer chain in a right, like a glycerol versus some simple solvent like cyclohexane, right, the friction is going to be different, right? When the friction coefficient is high in glycerol, for example, then the relaxation time is going to be longer. And if you take the polymer chain to be much bigger, the relaxation time is going to be even more bigger. So that intuitive argument is captured by this expression. Tau R is proportional to B friction coefficient times N squared divided by T. Please notice that it does not care about viscosity, right? The viscosity is not appearing here, except in this bead monomer friction coefficient. The viscosity of the solvent is not appearing, right, except for that frictional factor. Okay. And this is one of the major conclusions of the Rouse model. Okay, so as soon as you derive this expression, right, starting from here, you derive this expression, knowing the, right, you write down the Langevin equation for a flexible chain without any extra volume interaction, right? Just generalize what we wrote down for Brownian particle, but now the particle is a single segment, and you have an additional force coming from chain connectivity. If we put all these things, you know the probability distribution function, therefore you know the free energy of a particular conformation, take the force coming from the conformation, you get this equation, and then you have a very simple partial differential equation, and go to Fourier transform, namely Rouse transform if you like, then you get this physical description, and you have this expression. As soon as you have this expression, you have the relaxation spectrum. Okay, so this is a method. Okay, so instead of giving you a derivation of various quantities, I'm going to make a summary of the consequences of this equation. First, what is the value for center of mass motion? Okay, for the center of mass motion, or center of mass at time t minus r center of mass at time 0 squared is equal to 6 dt. Okay. And it works out that d center of mass is equal to kbt divided by zeta n. So the diffusion coefficient is inversely proportional to number of segments. Okay, this is not Stokes-Einstein. Please remember this. There is d center of mass. It's not Stokes-Einstein here, right? Here there is no radius of the polymer appearing here. In this model, every monomer is creating friction. The total amount of friction is zeta times n. There are n monomers. For each monomer, you have a friction coefficient zeta. The total friction is this. Therefore, kBT by total friction coefficient is the center of mass diffusion. This is Rouse. Okay. Then what we'll do is we'll look at locally. Suppose I label one of the monomers, right? So going back to this picture that I wrote down a long time back, this is our goal. This is center of mass motion. Center of mass motion follows the diffusion. Now I want to know how this monomer is going to move, label the monomer. So let me calculate, possible, easy to calculate the motion of a labeled monomer, Rm at t minus Rm at an earlier time. Let me calculate mean square displacement of that. If we do this, this becomes square root of t. Okay. Please notice that this is not Einstein's diffusion. And the reason is, right, the reason is quite obvious, right? So here is my polymer chain, like this, and I'm looking at, so the motion of, say, the mth monomer, it'll undergo diffusion, like, because in a medium where we are solving the stochastic equation, Brownian motion problem, but except now, right, if it's completely free, if it is not connected to its neighbors, the mean square displacement of that monomer would be proportional to time. That's Einstein's law. We talked about it, right? But now the situation is different. Now the situation is that this is connected to its neighbors. When it's connected to its neighbors, then its diffusion or the diffusive tendency is modified by the chain connectivity. Therefore, what happens is you have an additional contribution controlling its dynamics for times which are shorter than Rouse time. This is for t shorter than t tau Rouse. But if you wait long enough, right, if you wait long enough, then this is going to follow very much like center of mass motion. So here is your center of mass. That is your center of mass. The chain is going to move around, but if you look at time scales where the chain has completely relaxed, then, so for t larger than tau Rouse, right, this will go like t. If I label one of the monomers and watch for short enough times, short enough means compared to tau r, then you'll have this unique dependence on time. But then if you wait a very long time, then the motion of that monomer is same as that of the center of mass, because you're looking at very large scale. Suppose you look at some human being on Earth, and for very long times, when you look at the motion of that person, that's going to be same as the motion of the planet. You don't, right, for very long times. But when you go very close to that person and watch that person, he or she will be moving around with appropriate dynamics, and that's what happens in here. But this is for times below tau Rouse. But if the time is extremely short, so that this monomer has not had enough time to feel the force coming from the neighbors, then it'll be more like a Brownian motion problem, right? Because this has had not gotten enough time for it to feel, for it to be subjected to the force coming from its neighbors. Therefore, what I can do is I can draw a cartoon, a sketch. Okay, let me plot logarithm of t. This is Rm t minus Rm 0 square average. Let me take a double logarithm of this quantity versus logarithm of this quantity, time. If I do this, what I'm trying to tell you here is I have the square root of t behavior. So slope is half. And for very long times, that is after the Rouse time, I will follow the center of mass motion with a slope of 1. That is Einsteinian-like for very, very long times. For time larger than Rouse time, I'll have a slope of 1. But as I pointed out, for extremely short times, there is a regime for very, very short times. Let me call monomer relaxation time. Monomer, roughly, monomer relaxation time, which is extremely short. Within this time, the monomer has not had experience from the other neighbors. It is not yet influenced. It's trying to undergo Brownian motion, right? And therefore, as a consequence of that, there will be a slope of 1. Yeah. These things are very difficult to observe in experiments. But if you do computer simulations, you will see these 3 regimes. For very short times, you'll see a slope of 1, which is not significant. And then you get a slope of half, which is important. That's a signature of a Rouse chain. And then asymptotically, for very long times, you will get the Einstein results of diffusion. And then the monomer, every monomer follows the center of mass motion. You can observe only the center of mass motion. Therefore, you are not extracting the dynamics for very long times about that single monomer. Okay, but this is the year mark of Rouse. If you see this, you can confidently say you have Rouse dynamics. The slope is half. This is the year mark. This is a signature of Rouse dynamics. If you look at mean square displacement of monomer. Okay. Now what I like to do is I like to connect this with experiments. Okay, because you write the Rouse equation, you make Rouse model, you make the Rouse equation, and then solve it exactly. Then you get these conclusions. And of course, I can measure center of mass motion and find the diffusion coefficient. But we can also interrogate the internal dynamics of the polymer chain. And that's the nice thing about the attribute of polymer is that it has lots of internal dynamics. Remember, going back to the introduction, I told you that this is a rigid particle, right? Previously, we talked about rigid spherical particle. So we are not going to talk about rigid spherical particle because we are interested in flexible polymer chains. So we want to explore internal dynamics. When we do this, we get this information. We get this information. So how do we measure these quantities? Right. One of the ways you measure this quantity is incoherent dynamic structure factor. You measure it with incoherent dynamic structure factor. Right, S incoherent KT. Okay, and this K is scattering wave vector, as we've seen many, many times. And we can show that for T larger than tau R, sorry, for times larger than Rouse time, this is Rouse time, right? And you know what Rouse time is? That is proportional to n squared. For T time larger than Rouse time, this S KT goes like e to the minus d center of mass k square t. Exactly the way we saw for Brownian motion, Brownian particle. Remember, we looked at the experimental data, right? Experimental data for a Brownian particle. And we, there's a rate of decay. S of kt goes like e to the minus d center of mass k squared t. That means what's decay rate is a gamma k, that goes like a d center of mass k squared. So it undergoes diffusion, right? For T larger than tau R, we have diffusion. Now, going back in here, for T time shorter than tau R, we don't have diffusion. We have sub-diffusion, or due to chain connectivity, it's a very different dynamics. Therefore, for T less than tau R, and I'm going to ignore this uninteresting region. This is not that important. This is important only for people who do simulations. Experimentally, this is not of significance. So I'm going to ignore this region, right? So for T less than tau R, we are able to see, we explore internal chain dynamics. Okay. Now when we do this, S of incoherent KT goes like e to the minus, okay, k to the 4 t square root. Okay. So basically this goes like e to the minus k square root of t. And whenever you see e to the minus k square or e to the minus something which is not t, right? If it's a t, it's exponential, right? E to the minus t. When it is not e to the minus t, and if it has e to the minus t power some exponent, in this particular case, that exponent is half. We call this to be stretched exponential. We call this to be stretched exponential. E to the minus, instead of t, which is exponential, now we have t power some exponent, say, in this particular case, it's half. But the important thing is here is the decay rate goes like k to the 4. In the case of diffusion, for very long times, decay rate goes like k squared, right? It goes like k squared for the diffusion. But here, the decay rate goes like k to the 4. If you make measurements using neutrons or X-rays, and if we explore what happens inside the polymer chain, incoherent structure factor, if you find a decay rate going like k to the 4, you say it undergoes Rouse dynamics. So this is the signature of Rouse dynamics. K to the 4 behavior is signature of Rouse dynamics, which is intimately related to the fact that mean square displacement goes like square root of t for short times. Mean square displacement here goes like square root of t for short times. And as a consequence of this, you get the decay rate going like k to the 4. Okay, so now these are all predictions of Rouse model. Single chain, right? This is a Rouse model. Now let's go to another experimental experiment, which is, make a viscosity, make measurements of viscosity and moduli, right? Let me focus on viscosity. The prediction of the Rouse model is for the viscosity, remember the single chain, we are talking about single chain, right? Remember, we defined the intrinsic viscosity. Intrinsic viscosity. Intrinsic viscosity, let me give a symbol, this one. This is, in a dilute solution limit of polymer concentration going to be small, right? Viscosity of the solution minus viscosity of the solvent divided by viscosity of the solvent times the C. That is the definition of intrinsic viscosity. So when we do the calculation based on Rouse model, the answer turns out to be, this turns out to be equal to Avogadro number divided by molar mass times viscosity of the solvent, zeta n square L square divided by 36. That's the way it turns out. This is intrinsic viscosity. The intrinsic viscosity, if you work it out, where this is Avogadro number molecular weight and we know friction coefficient of the monomer. That's important. Friction coefficient of monomer times n squared. And here is molar mass. And the n number of segments is proportional to molecular weight. Therefore, what we see is, therefore, what we get is eta minus eta naught divided by eta naught is going like, right? Eta minus eta naught divided by eta naught is going like this, a factor of C. And then here is the zeta, n squared by m. Therefore, what I get is C, zeta, and molecular weight. Proportional. So this is the equation this is an important result that we get for change in viscosity. Change in viscosity according to Rouse model is proportional to concentration, proportional to segment friction coefficient, and proportional to molecular weight. Because this is something we can measure. We can measure and compare and see how good the Rouse model is. Okay. So these are the key aspects of a Rouse model. So what we have done is we have calculated a Rouse spectrum by making a derivation. We have calculated the Rouse spectrum. This is an important quantity. And then that gives me a time scale for this problem, which is a Rouse time. which tells me a clock. Is my timer measurement short? Is my timer measurement long? It's all dictated by this Rouse time, which in turn depends on molecular weight and temperature. Then I can design my experiment. Once I estimate what the Rouse time is going to be for a given molecular weight, then I can design my experiment about under what conditions I can explore internal dynamics of the chain, under what conditions I can explore the global motion of these polymer chains. Okay, therefore, this is a very important quantity, critical quantity. We need to know, we need to have a clock. We need to have a characteristic time for the particular choice of my model, right? But once I have this, we can explore experimentally, we can measure mean square displacement of center of mass. We can explore mean square displacement of labeled monomer. We can also measure using scattering techniques for very long times and also shorter times. And the behaviors are very different. We can also make measurements of the bulk. We can measure the viscosity of a solution. And for all these things, there are very, very clear, exact predictions. Okay. Okay, now I need to make a reflection of what we did. All right, what we did. Let me make a summary of what we have accomplished. This is a conceptual argument because you have the data, I mean, the derivations and the explicit expressions for the important quantities in front of you. But let's make a kind of a general conclusion. Let me make a comparison between two situations. Okay. One situation is Einstein's Brownian particle. Okay. And other one is Rouse. Okay. So what did we say for the Brownian particle? We said center of mass at time t minus r center of mass at an earlier time square average, that's equal to 6 dt if t is larger than tau. That tau was m over zeta. If you go back and look at it, right? We had that. Right? When t is larger than tau, we got the diffusion. And then we said this diffusion coefficient is equal to kBt by 6 pi eta naught r, where r is the radius of the particle. Okay. And then we said change in viscosity eta minus eta naught by eta naught went like, right, a volume fraction, right? That went like number of chains n over v times r cubed. Number of particles, n is number of particles. This is number concentration. Number concentration. That's what we did. These are the three important quantities we did. And then there is no internal structure because there is a rigid particle, there's no internal structure. Okay. Now let's look at let's contrast that with Rouse model. In the Rouse model, we also have r center of mass at time t minus r center of mass at an earlier time square. That's equal to 6 dt again. For t, right, for t larger than t Rouse, and then t Rouse, tau Rouse, that goes like n squared. It depends on n squared, right? Go back here. Tau r, where are we? Tau r goes like n squared zeta by t. Please notice in Einstein's problem, there is no molecular weight square. Here, n is molecular weight. Here is mass, which is related to molecular weight of that particle, right? Look at the difference. The characteristic time is entirely different, right? And please look at here, zeta appears in the denominator, and here zeta is in the numerator. And the temperature appears here, right? In terms of relaxation time, there is no temperature for relaxation time. Here, the temperature, the entropy of the polymer chain appears in here. That's how we get this T. This T comes because of this quantity, right? When we wrote down this free energy, there's a temperature there. This is entropy contribution. And that's how chain connectivity, that's how we get this temperature dependence. For T larger than this, we get. Then what we get is, okay, in addition, we get a D, the center of mass, is going like, right, please, kBT divided by zeta n. The radius of the polymer does not appear. Radius gyration does not appear. Only the molecular weight appears here. In Einstein's problem, you know, since it's a rigid sphere, if you want to write into the molecular weight, that R would go like molecular weight power 1/3, because rigid sphere, R cubed, that's the volume, that will be proportional to the mass, right? We don't have that. We had kT by zeta n. Okay. Now let's go and look at the change in viscosity. The change in viscosity goes like eta minus eta naught by eta naught is going like, right? I told you C, right? Going back to the previous slide, C zeta n. C zeta n. I wrote down C zeta n, apart from the prefactors. But now you know C is, right? You know the C is equal to number of chains, molecular weight, or we write N divided by V. That's our monomer concentration. In this expression, C is a monomer concentration. Therefore, what I get is, I get viscosity going like, in this notation, N over V zeta N squared. If I write it up, now this is number concentration, right? N over V is a number concentration. If I write in terms of number concentration, right? I have, instead of R cubed, I have zeta times N squared. Please look at the distinct difference between Einstein's expression and for our polymer case. Here, in the Einstein's case, there is no friction coefficient appearing here. For the change, it only depends on volume. Here, there's no volume. It's the N square and friction coefficient here. So therefore, what we have is here two different classes of problems, it seems, right? That's what it seems like. But I want to tell you that, there is something that's not quite right. Okay. We did the Rouse calculation exactly, but it is not consistent. The predictions are not consistent with a single chain, because we will expect, I'll convince you, I told you in the last lecture, that the predictions of Einstein's laws can be generalized to polymer chains also in dilute solutions. Because we are talking about one object that is floating around. And that's a norm, right? Now what we have is, right? What we have is similar situation, but we have a model for polymer chains, and the predictions of this Rouse model are not consistent with the predictions that we would get from Einstein's description or a Brownian particle description. Where are we going wrong? Why? What's missing in the description of Rouse model? Right. First of all, we have to go and make measurements, right? Measurements of dilute solution. And we can measure how does this viscosity go in dilute solutions. I can tell you that this is not seen. For a Gaussian chain, which is theta condition, we do not see that. And when you make measurement of diffusion coefficient of center of mass in dilute solutions of a Gaussian chain condition, we do not see this, right? So what is missing in this Rouse model? Because we did the calculation exactly. Okay. That takes us to the next topic, next chapter. And I'm going to discuss the next one in a detail next week. And before that, I want to mention what is missing. What is missing is the following. If you take a dilute solution, before that, I meant to say, look at this one, diffusion coefficient, right? So there is in Einstein's calculation, there is a viscosity of the solvent, right? D kT by 6 pi eta and R. Here, exact calculation shows kT by zeta n. There is no viscosity in here, right? This is just a bit friction coefficient, right? That actually is a clue. So what is missing here is the following. Imagine a situation in a dilute solution like this. Your chain is like that. This is in a solvent. In a solvent of viscosity eta naught. So let's imagine a scenario where this monomer is moving. This monomer is moving. When the monomer is moving, what it does is it creates a force in the fluid. Imagine you are in a swimming pool, right? And you are swimming, and when you swim, when you make motion, you are creating waves around you. So because of that perturbation you are making in the fluid, it creates a wave. It can go everywhere. It can go and affect this monomer. It can go affect this monomer. It can go affect that monomer. It can go and affect all these monomers in here. So, and as a result of that, that monomer will also feel an extra additional force. In addition to the connectivity that we had in here and a random force, there is also hydrodynamic of, this is what we call hydrodynamic force. Hydrodynamic force goes there, and goes there. Excuse me for a second. Just 1 second, please. Let me, I don't know, I want to. Just excuse me, I don't know what happened. So, okay, so anyway, there is going to be hydrodynamic forces here, which is going to be affecting this various monomer. This monomer will be affected, that monomer will be affected, that monomer will be affected, all of them would be affected. Okay? But not only that, these monomers, right, once they are affected, these monomers would also send in hydrodynamic forces. That is going to create, imagine I have lots of boats on a lake. One boat makes some perturbation, and that is going to create some waves. It's going to affect another boat, and the another boat is going to create some waves. That's going to affect. So they will all come and affect, and in fact, they can also come back and affect it here too. This is what we call hydrodynamic interaction. hydrodynamic interaction. And this is a subject that we are going to talk about in the next lecture. So we need to account for this hydrodynamic interaction among all monomers, among all segments of the polymer chain, in addition to what we talked about. Even for a Gaussian chain, forget about extra volume interaction for the time being. Even for a Gaussian chain, in addition to chain connectivity, we must include this. This is done what is called ZIM model. This is what we are going to talk about in the next lecture. In fact, this was done even prior to ZIM, and in reality, it should be called Kirkwood-Reisman model. This was done 10 years ahead of before ZIM. So let's call Kirkwood-Reisman the ZIM model. This is only an introduction. Please brush up your knowledge about hydrodynamics, and I'll have a very brief introduction about hydrodynamics, and then we'll include that without doing too much algebra or mathematics. We will talk about the consequences of including hydrodynamic interaction in our description. Okay, this is where I like to stop, and I'll take some questions from you folks if you have anything.